Okay, let's unpack this. Imagine the scene. A storm rolls in, sky darkens, and then wham, that sudden blinding flash followed by that earth-shaking clap of thunder. It's one of nature's most dramatic, raw performances.
It really is visceral, powerful, something that just grabs your attention instantly. And it feels a bit mysterious, doesn't it?
Absolutely. And that mystery is exactly what we're diving into today. We've taken a stack of source material, this really comprehensive deep dive into the science of lightning, and our mission basically is to cut through the complexity, pull out the most important insights, and figure out exactly what this incredible natural thing is, how it works, and its surprising impact on everything from geology to atmospheric chemistry.
Yeah. Think of this as your shortcut to understanding lightning in a whole new way.
We're going to guide you through the science, the different forms lightning takes, the still unfolding story of how it's created, its unexpected effects, and even its deep roots in human culture.
You'll walk away remarkably well-informed about something you see every time a storm rolls in. Hopefully.
So let's start with the absolute basics. When we see that flash, that intense burst of energy, what fundamentally is lightning?
Well, at its most basic level, lightning is a natural electrostatic discharge. It's nature's way of suddenly equalizing electrical charges that have built up between different regions.
Usually within a storm cloud.
Often, yeah, or sometimes between the cloud and the ground.
And the amount of energy involved is just staggering.
It truly is. The source material points out the energy release in a single flash typically averages between 200 megajoules and, get this, 7 gigajoule.
Well, what does that even mean in real terms?
Well, to give you a sense of scale, that's enough energy to power a typical American home for several weeks, released in, less than a second.
Which explains why the air around that channel gets unbelievably hot.
Precisely. We're talking rapid heating to temperatures around 30,000 degrees Celsius. That's over 54,000 degrees Fahrenheit.
Whoa.
Much, much hotter than the surface of the sun.
And that extreme heat and rapid expansion of the air is what creates the two things we always notice, the flash and the thunder.
Right. The flash is the superheated plasma channel radiating electromagnetic energy, including, obviously, visible light. And that incredibly rapid, almost explosive expansion of the air along the channel generates a powerful shock wave.
Which we hear as thunder.
Which we perceive as sound thunder.
Yeah, we usually think of lightning happening only in thunderstorms. But it's a bit more versatile than that, isn't it?
It is. While thunderstorms are the most commonplace, lightning can also occur in other energetic atmospheric events, like volcanic eruptions, intense dust storms.
Really? Dust storms?
Yeah. And even during massive wildfires, which can create their own storm clouds called pyrocumulonimbus.
Fire thunderstorms, basically.
Kind of, yeah. You can also see it in tornadoes. During heavy snowstorms, they call that thundersnow, and sometimes in the rain bands of hurricanes, too.
So it's not just a thunderstorm thing, it's more like an intense atmospheric energy thing.
That's a good way to put it. And its impact goes way beyond just putting on a show.
Right.
Absolutely. Lightning plays a significant role in Earth's atmospheric electrical circuit globally. It influences atmospheric chemistry, for instance, by creating nitrogen compounds.
Okay.
And it's a major natural ignition source for wildfires. It's such a fundamental part of the Earth system that it's classified as an essential climate variable.
Wow.
And there's a whole field of science dedicated to studying it called fulminology.
Fulminology, I love that. There's a specific name for studying lightning. Okay, so we know what it is and where it can happen. Let's talk about the different ways it looks. The source material outlines the main forms based on where the discharge is taking place.
Right. So the most frequent type, believe it or not, you might not even hear clearly. It's called intracloud or IC lightning.
Intracloud.
Happening entirely within a single storm cloud.
Ah, is that the flash you sometimes see in the distance at night, illuminating the cloud from within, where you don't hear a distinct thunderclap?
Exactly. Or sometimes that's cloud-to-cloud lightning or intercloud lightning, where the discharge jumps between two separate storm clouds.
Okay.
From far away, without hearing the thunder, it just looks like a sheet of light, hence the common term sheet lightning.
Got it. And then there's the one we're perhaps most focused on, the one that poses a direct threat.
That's cloud-to-ground lightning, or CG. This is the discharge between the cloud and the Earth's surface. It's what we universally call a lightning strike.
Right.
It's actually the least common of the three main types globally, but because it terminates on the ground, it's the easiest for scientists to study directly and critically. It poses the greatest danger to people and property.
Makes perfect sense. That's the one that can ruin your day or worse. Now, even cloud-to-ground lightning isn't all the same. There's negative and positive CG.
That's right. That's determined by the direction of the conventional electric current flow between the cloud and the ground. Over 95% of CG lightning is negative, meaning negative charge effectively moves downwards. In a positive flash, positive charge is effectively transferred downwards.
And positive lightning has a reputation for being particularly nasty.
It does, and for good reason. An average negative flash involves currents around 30,000 amperes and transfers about 15 coulombs of charge. But large positive flashes, well, they can reach 120,000 amperes and transfer up to 350 coulombs.
Whoa.
The source material highlights that average positive flashes have roughly double the peak current of typical negative ones, and in extreme cases, peak currents can reach up to 400,000 amps and several hundred coulombs.
Wow. So significantly more powerful. Why does that make them more dangerous on the ground?
It's not just the peak current, it's also that positive flashes often have longer duration continuing currents after the initial peak.
Okay.
More current for longer means significantly more heating, which greatly increases the risk of ignition and starting fires.
And aren't positive flashes also responsible for those seemingly random strikes? The ones out of nowhere.
Yes, the infamous bolts from the blue. These are often powerful positive lightning flashes that appear to come from the edge of a storm, even where the sky seems relatively clear, or maybe from the storm's anvil cloud.
Okay.
They can travel long distances horizontally through the air before turning down to strike the ground, giving very little warning.
So they really do live up to their name.
Mm.
The source mentions a nuance about these bolts from the blue, though, right? Something a bit counterintuitive.
Yes, exactly. There's a common misconception that all bolts from the blue, especially those from the anvil, must be positive lightning originating from the storm top's positive charge region.
Right, that makes sense.
But observations have shown that many of these distant strikes, even those appearing to come from the clear air near the anvil, are actually negative flashes.
Negative? How?
They started as intra-cloud lightning within the cloud and then traveled a long distance horizontally before exiting the cloud and turning downwards as a negative strike. So while they looked like they came from nowhere or the clear air, they might have originated quite differently than you'd first assume.
Fascinating. It's always more complex than it looks.
Mm.
You also mentioned anvil crawlers earlier when talking about cloud lightning. What are those?
Yeah, anvil crawlers. They're a really dramatic form of intracloud or cloud-to-cloud lightning. It's where the charge equalization process spreads horizontally through the upper layers of the storm, particularly the anvil cloud.
So you see it spreading out across the top.
Yeah, you see those multiple branching channels of light appearing to crawl across the sky. Often when a storm is moving away or dissipating, they really highlight the vast horizontal scale of charge separation in these storms.
Okay, so that covers the different forms lightning takes. But the real mystery, the part that still feels like magic, is how. How does all this electrical charge build up and eventually discharge? What's the step-by-step process?
It is complex, and scientists are still refining their understanding of some steps. But the source material outlines 4 main categories of processes involved. First, you need the right atmospheric conditions.
Like a lot of unstable air, updrafts, clouds, storm stuff.
Exactly. Thunderstorms are the classic example, requiring warm, moist air rising and interacting with colder air. But as we noted, it's not only thunderstorms. Any phenomenon creating strong vertical motion and charge separation can potentially do it.
Like those volcanic ash plumes or intense wildfires.
Right. Those fires generate pyrocumulonimbus clouds capable of producing fire lightning or dry lightning, which can actually ignite more fires. It's a feedback loop sometimes.
The source also listed some really surprising potential influences, things I wouldn't have thought of.
Yes, things you wouldn't immediately connect, like airplane contrails maybe providing a pathway for charge, rocket exhaust plumes.
Didn't that happen with Apollo 12?
Famously triggered lightning during the Apollo 12 launch, yes. Even the complex charged environment created by thermonuclear explosions through something called Compton scattering.
Wow.
And intriguingly, the source mentions that high-energy cosmic rays and solar wind particles entering the atmosphere might electrify the air and potentially initiate conductive pathways.
Cosmic rays triggering lightning. That links weather events to forces from deep space. Okay, so you have the conditions. What's stir to?
Charge separation. This is perhaps the most studied and still somewhat debated part of the process. It's where different parts of the cloud become electrically charged, positive in some areas, negative in others.
How does that even happen inside a cloud? Just randomly?
Not randomly, no. The leading theory in thunderstorms focuses on something called non-inductive charging. This happens mostly in the core of the storm where there's a strong updraft and temperatures are between roughly -15 and -25 degrees Celsius.
Okay, what's special about that temperature zone?
It's where you have a mix of ice particles of different sizes. Specifically, lighter, rising small ice crystals and larger, heavier particles called gropal, which are like soft ice pellets falling downwards.
Right.
When these particles collide in the presence of supercooled water droplets, charge gets transferred.
Okay, so they bump into each other, and what happens to the charge? Which way does it go?
The crucial part is which way the charge goes. In this temperature range, when a small ice crystal collides with a larger gropal particle, the small ice crystal tends to become positively charged, and the larger gropal particle becomes negatively charged.
Ah, okay, so the collisions create the charge imbalance.
And the storm's motion separates them.
Precisely. The strong updraft lifts the lighter, positively charged ice crystals towards the top of the cloud, especially into the anvil region. The heavier, negatively charged gropal tends to collect in the middle and lower parts of the cloud.
Right.
This creates the dominant charge structure, a large positive region at the top and a large negative region below it.
And there's often a smaller positive pocket near the bottom, too.
Yes, usually a small positive charge region develops near the cloud base, likely due to warmer temperatures and precipitation particles. This gives the typical thundercloud a tripolar structure, positive at the top, negative in the middle, and a smaller positive at the bottom.
Okay, tripolar. Got it. The source mentioned other processes like inductive charging, too, briefly.
Those are other mechanisms that can contribute or be dominant in different situations. Things like charge separation induced by the Earth's existing fair-weather electric field or during collisions of liquid water drops. The source also touches on historical contexts, like Lord Kelvin's water dropper experiments, and the fundamental role of ions in water.
Right. Though the main discharge current, the big zap, is carried by electrons in the lightning channel's plasma.
All right, so we have these big, separated pools of positive and negative charge within the cloud. What's step 3? Establishing the field.
Exactly. Establishing the electric field, you've built up a huge potential difference, basically, a giant voltage between these separated charge regions.
Wow.
The air between them is normally an insulator. It stops the charges from just flowing freely.
Sure.
But the larger the charge separation and the closer the regions, the stronger the electric field gets. The source also notes that this charged cloud induces an opposite charge on the ground below it, concentrating positive charge directly under the negative part of the cloud, creating a localized, strong electric field between the cloud base and the ground.
And when that electric field gets too strong for the air to handle, when the air just gives up.
That's step 4. The electrical discharge the lightning itself. When the electric field strength exceeds the dielectric strength of the air, that's the point at which air breaks down and becomes a conductor, about 3 million volts per meter in human air, the discharge process begins.
So the air turns conductive.
And the source adds that this breakdown involves rapid electrochemistry, converting ions into the high-energy electrons that will carry the massive current.
Okay, so the air breaks down. How did that actually start the visible flash? It's not instantaneous, is it? I mean, it feels instantaneous.
No, it's not quite. It starts with the formation of something called a leader. This is a channel of ionized air, essentially a pathway where electrons are starting to flow, making the air conductive.
Okay.
How these leaders initiate is still a subject of active research, possibly linked to those high-energy cosmic rays we mentioned, or maybe areas of extremely enhanced electric fields near particles in the cloud.
So even the very first spark is still a bit of a mystery.
Some of the fine details are, yes. What we do know is that these leaders propagate outwards from the charged regions. A negative leader moves towards the positive region, and a positive leader moves towards the negative region.
And they sort of step down.
Downward leaders towards the ground often move in a stepped fashion, advancing in segments of about 45 meters or so at a time. That's why you sometimes see that jerky motion in slow-motion video. Establishing this ionized channel takes hundreds of milliseconds, which is slow in lightning terms, and involves relatively small currents compared to what's coming next.
So you have this stepping leader heading down from the cloud towards the ground. What happens as it gets close?
As the downward leader approaches the ground, the strong electric field concentrates even more at tall objects, trees, buildings, utility poles, even people standing out in the open.
Right.
This enhanced field can become strong enough to initiate upward-moving, positively charged channels called streamers from these objects.
Like fingers reaching up from the ground to meet the leader coming down.
That's a great way to visualize it. These upward streamers are more likely to launch from objects already experiencing corona discharge, that faint electrical glow you sometimes see on pointed objects in a strong electric field just before lightning strikes.
Oh, okay. Like St. Elmo's fire.
Similar principle, yes. This upward streamer concept was first theorized by physicist Heinz Casimir.
And when the downward leader connects with one of these upward streamers, then what happens?
That's called attachment. A complete low-resistance path is now formed between the cloud and the ground. The source notes you can sometimes see unattached leaders or streamers in photos or videos frozen in time just before they connect.
And that's when you get the incredible bright flash we see, the main event.
That's the return stroke, yes. It's the main, most powerful phase. Electrons from the ground rush upwards through that newly connected channel at incredible speeds, up to 1/3 the speed of light.
Wow.
This massive, rapid surge of current, average 30,000 amps for negative CG, effectively neutralizes the accumulated positive charge on the ground below the strike point.
And this surge is what creates the hidden danger on the ground, even if you're not directly hit. You mentioned this earlier.
Yes. This is where the concept of step potentials comes in, and it's really critical to understand. When that huge current hits the ground, it doesn't just disappear, it spreads out radially across the surface.
Wow.
Because the ground has electrical resistance, this spreading current creates significant voltage differences along the surface. Different points on the ground have different electrical potentials.
Voltage differences on the ground. How is that dangerous?
Imagine the ground surface as having varying electrical pressure. If you're standing with your feet apart near a strike, maybe a few yards away, your body can bridge 2 points on the ground with a large voltage difference between them.
Oh, I see.
The electricity will then flow up one leg, potentially through your torso, and out the other leg, seeking a path to equalize the potential. This can cause severe internal injury or death.
That's terrifying.
It's why being in a group and holding hands or standing near livestock in a field is particularly dangerous. The current can pass through multiple bodies. Electricity takes all available paths, unfortunately.
That's something I think many people don't realize is a major risk. So the return stroke is this massive surge heating the channel.
Yes, the channel core instantly becomes a superheated plasma, reaching over 27,800 degrees Celsius. Again, hotter than the sun's surface.
Incredible.
This plasma is incredibly luminous, producing the brilliant flash. As the current decays, the channel cools and the air rapidly contracts, which creates that shock wave we hear as thunder.
And we often see flashes flicker or repeat, right? It's not just one bang.
That's due to multiple strokes within a single lightning flash. Most negative CG flashes aren't just one event. They typically have 3 or 4 return strokes, but sometimes up to 30 separated by tens of milliseconds, usually around 40-50 meters.
And that's what gives that flickering or strobe-like effect.
Exactly.
And subsequent strokes reuse the same path.
Usually, yes. Each subsequent stroke is often initiated by a dart leader that travels quickly down the original ionized channel left by the previous stroke. Wind might offset it slightly, making it look a bit different. The source notes that, interestingly, positive ground flashes much less frequently have these multiple strokes using the same channel. The dart or recoil leader process that follows negative leaders doesn't really happen with positive ones.
So negative lightning is the one that tends to flash multiple times up that same channel. What about other electrical effects from the rapid current changes, surges and stuff?
Those are significant. They're called transient currents. The current rises incredibly fast in a negative CG strike, peaking within just 1 to 10 microseconds, and then decays more slowly.
Microseconds.
Yeah. This rapid change in current causes several effects. One is the skin effect, where high-frequency or rapidly changing currents tend to flow mostly on the surface of a conductor. That's why lightning protection systems often use multi-stranded cables to maximize surface area.
Okay, makes sense. And the other big effect, EMP.
Electromagnetic pulses, or EMPs, yes. The rapid current changes and high voltages radiate powerful electromagnetic waves outwards. If these waves interact with conductive lines like power lines, phone lines, internet cables, even underground metal pipes, they can induce transient currents and voltages.
The surges that can fry your electronics, even if the lightning didn't hit your house directly.
Exactly. That's a common consequence of lightning, even from indirect strikes some distance away. Surge protection devices, or SPDs, are designed to detect these rapid voltage spikes and divert the excess current safely to the ground before it reaches your sensitive equipment.
That's an incredible amount of complexity happening in that split second we see a flash. Let's zoom out from the single strike. How often is all this happening around the planet, and where are the hotspots?
Globally, well, lightning detection networks estimate that lightning occurs about 44 times every single second, on average.
44 times a second. Wow.
Yeah, that adds up to around 1.4 billion flashes per year. The median duration of an entire flash sequence, including all those multiple strokes, is about half a second.
Constantly happening somewhere. But it's not spread evenly across the globe, right?
Far from it. About 70% of all lightning flashes occur over land in the tropics.
Wide there.
That's where you have the most intense solar heating, leading to the strongest atmospheric convection and the deepest, most energetic thunderstorms. Factors like ground elevation, latitude, wind patterns, humidity, and proximity to large bodies of water all influence where and how often lightning occurs.
And that proportion of dangerous cloud-to-ground strikes varies geographically, too.
Yeah.
You mentioned only 25% globally hit the ground.
Yes. That percentage changes with latitude. In the tropics, only about 10% of flashes hit the ground.
Why so few?
Largely because the freezing level in the atmosphere, where that key charge separation happens, is higher up, so the charge is further from the ground. But as you move poleward to places like Norway, around 60 degrees north, where the freezing level is lower, up to 50% of flashes can be cloud to ground.
Okay, where are the absolute busiest lightning spots on Earth? Like, where would you definitely want a good lightning rod?
Well, the source highlights a few famous ones. Lake Maracaibo in Venezuela, known for the Catatumbo lightning, can see an average of 250 flashes a day, nearly 300 days a year. It's almost constant there.
Incredible.
Kifuka in the Democratic Republic of Congo has one of the highest strike densities, averaging 158 strikes per square kilometer per year. Singapore and Central Florida, known as Lightning Alley, are also well-known hotspots for intense lightning activity.
And we've seen some incredible record-breaking flashes recently, haven't we? Mega flashes.
We have. The World Meteorological Organization recently verified a mega flash in the southern U.S. in 2020 that covered a horizontal distance of 768 kilometers. That's almost 477 miles.
That's insane. A single flash that long?
A single flash event, yeah. And another record flash in Uruguay and Argentina in 2020 lasted an astonishing 17.1 seconds.
17 seconds.
These events are really pushing the boundaries of what we thought lightning could do.
Incredible scale. How fast are those stepping leaders actually moving towards the ground before the big return stroke?
Near the ground, step leaders typically move at speeds ranging from about 100,000 up to 1.4 million meters per second. The average is around 440,000 meters per second.
Still incredibly fast, but much slower than the return stroke itself.
Orders of magnitude slower, yeah.
It's easy to feel like lightning is just an Earth thing, but it's a phenomenon that happens off-world too, right? On other planets.
It is. Lightning has been observed and detected on other planets with substantial atmospheres and active weather systems, notably Jupiter and Saturn.
Jupiter and Saturn.
Yeah, and it's likely present on Uranus and Neptune as well. Jupiter's lightning seems to be even more energetic than Earth, so the basic mechanism appears similar. Although recent findings suggest a new type, potentially linked to ammonia-rich structures called mushballs in its atmosphere.
Mushballs.
Yeah, that's the term. Voyager 1 was the first mission to detect lightning on Saturn back in the day.
What about Venus? I feel like I've heard conflicting things about Venus having lightning.
Venus is definitely a more controversial topic.
Yeah.
Early missions like Venera and Pioneer reported possible detections, suggesting lightning activity. However, the Cassini mission, which was designed to be very sensitive, saw nothing during its Venus flybys. More recently, the Venus Express mission detected radio pulses that could be attributed to lightning, so the scientific community is still debating and gathering evidence. It's not settled yet.
Okay, let's talk about what happens because of all this energy. Beyond the obvious flash and bang, what are the effects of lightning? What does it do?
The effects can be immediate and temporary, like the light and sound, or they can cause long-lasting physical damage and environmental changes.
Starting with nature trees, the ground. What happens there?
Well, the intense heat can instantly vaporize moisture within a tree, causing the bark to be explosively ripped off or the trunk split wide open. You see that sometimes? It can heat water trapped in cracks and rocks, causing them to fracture further. And, of course, lightning is a primary natural cause of wildfires, especially those intense events sparked by fire lightning or dry lightning.
And it can create those weird glass tubes in sand.
Fulgurites, yes. In sandy soil, the incredible heat from a strike can fuse the sand grains together into unique glass-lined tubes that trace the path of the lightning into the ground.
I've seen pictures of fulgurites. They're amazing natural sculptures and on buildings and structures.
Buildings are obviously vulnerable as lightning seeks the easiest, most conductive path to the ground. That's why lightning protection systems, like traditional lightning rods, are installed. They provide a preferred, safe pathway for the current to travel to the earth without damaging the building's structure.
But even with rods, there are risks.
Oh, yes. Buildings are still susceptible to indirect effects like fire risk from secondary sparks and damage to electrical systems from those transient surges we discussed earlier. Surge protection devices, SPDs, are essential for mitigating that risk to electronics inside.
What about airplanes? They seem like giant metal targets flying through storm clouds.
They are struck relatively often, actually, but they are designed to be safe. The metallic fuselage acts effectively as a Faraday cage, directing the electrical current around the outside of the passenger cabin.
So the people inside are generally okay.
Usually, yes. Modern aircraft incorporate features to handle strikes safely, and often passengers don't even know they've been hit. However, there are documented risks like temporary pilot disorientation or blindness from the intense flash, and historical concerns about fuel ignition, though aircraft design has significantly reduced that specific risk now.
And sadly, the effects on people and animals on the ground.
The risk of severe injury or death is real, due to potential damage to the nervous system and internal organs from the electrical current. However, the survival rate for people struck by lightning is surprisingly high, around 90%.
90%? That's higher than I would have guessed.
It is. But as we emphasized earlier, the danger of step potential spreading out along the ground is particularly significant. That often injures or kills groups of people or animals standing near a strike point, even if they aren't directly contacted by the lightning channel itself.
Let's revisit thunder for a second. Why does it sometimes rumble for a long time instead of just being a sharp clap?
That's because the sound waves are generated along the entire length of the lightning channel, which can be miles long, right?
Sure.
Different parts of that channel are at different distances from you. So the sound from each part arrives at your ears at slightly different times, creating that drawn-out rolling or rumbling effect.
And that's the basis for figuring out how far away a storm is.
Right.
The flash-to-bang time.
Exactly. Light travels almost instantaneously for our purposes, but sound is much slower. You count the seconds between seeing the flash and hearing the start of the thunder. Every 5 seconds you count means the lightning was roughly 1 mile away.
Or 3 seconds for a kilometer.
Roughly, yes. 3 seconds per kilometer. A sharp, immediate clap means the lightning was very close. A long, low rumble means it was farther away. And if it's really close, you might even smell ozone, that clean, sharp scent.
Yeah, that distinctive smell. Beyond visible light and sound, what other forms of energy does lightning emit? Radio waves.
It emits radio waves as pulses, yes. Specifically, very low frequency, VLF, and extremely low frequency, ELF waves. What's fascinating is that these specific wavelengths get trapped between the Earth's surface and the ionosphere.
Like a tunnel.
Essentially, yeah. The Earth ionosphere system acts like a giant waveguide. This allows these VLF-ELF signals to travel thousands of kilometers around the planet.
And this is how lightning detection networks work globally. They listen for these waves.
Yes, exactly. Ground-based networks listen for these VLF-ELF signals to locate strikes and estimate their properties. Global patterns of ELF radiation even allow scientists to monitor overall worldwide thunderstorm activity. These influence what are called Schumann resonances.
Schumann resonances.
Yeah, it's like the Earth ionosphere cavity ringing like a bell from all the lightning. The environment around a strike also subtly changes the shape of these radio signals, providing even more data.
And the source mentions even higher energy radiation. X-rays, gamma rays.
Yeah.
This was one of the most surprising parts to me.
Absolutely. It's pretty mind-blowing. The existence of X-rays from lightning was actually predicted way back in 1925 by C.T.R. Wilson, but wasn't definitively detected until 2001 and 2002.
Wow.
Both from artificially triggered and natural lightning leaders. This is still an area of active research because the temperature of the lightning plasma itself isn't actually hot enough to produce these X-rays, according to standard thermal physics.
So something else is going on.
Something else must be accelerating particles to high enough energies. And even more incredibly, space-based telescopes have detected terrestrial gamma ray flashes, or TGFs, originating from thunderstorms.
Gamma rays, like radioactive decay level energy from lightning.
Yes, TGFs are the most energetic natural phenomenon originating from Earth. They are incredibly brief and intense bursts of gamma rays, somehow linked to the strong electric fields in thunderstorms.
That's wild.
And the source points out something truly mind-boggling that's come out of this research recently. Detection of antimatter signatures, specifically positrons being produced by lightning.
Wait, lightning can produce antimatter. The stuff of science fiction. Positrons.
According to the source material on TGFs and associated phenomena, yes, there's clear evidence of positrons, the antiparticles of electrons being generated,
Oh.
likely through complex interactions of high-energy electrons accelerated in the storm's electric fields colliding with air molecules. This is one of those areas that is still actively challenging and expanding our understanding of atmospheric physics. It's really cutting-edge stuff.
That is just mind-bending. From colliding ice pellets to producing antimatter.
Wow.
Okay, beyond these temporary energetic effects, lightning also leaves some longer-lasting marks on the environment, doesn't it?
It does. The extremely high temperatures and electrical breakdown within the lightning channel significantly alter the local chemistry of the air.
How so?
It increases the concentration of ozone and especially oxides of nitrogen, or NOx. A single flash in temperate areas produces about 7 kilograms of NOx.
7 kilograms from one flash.
Yeah. And this affects the atmosphere on a larger scale. This lightning-produced NOx contributes significantly to increasing overall tropospheric NOx levels, maybe by up to 90%, according to some estimates, and ozone levels by up to 30%. This plays a role in atmospheric chemistry and air quality.
But it's also beneficial in another way, right? Something about fertilizer.
Correct. Lightning plays a crucial role in the natural nitrogen cycle. It oxidizes atmospheric nitrogen gas, which is pretty inert, into nitrates.
Okay.
These nitrates are then carried down to the Earth's surface by rain, and these nitrates are a vital nutrient for plants. It's essentially nature's way of fertilizing ecosystems.
So lightning helps feed the plants, and it can leave a permanent mark on the ground itself, like a geological fingerprint. Magnetism.
Yes, through a process called lightning-induced remnant magnetism, or LIRM. The intense, fleeting magnetic field generated by the huge current of a lightning strike can permanently magnetize susceptible minerals in rock, soil, or even metal artifacts along its path.
Permanent.
Yeah. The magnetization follows the path of least electrical resistance, which might be vertical straight down, or it could be horizontal, following things like geological faults or water tables underground.
So you could potentially find where lightning struck ages ago by looking for magnetic anomalies in the ground.
Exactly. Geologists and archaeologists can use magnetic surveys to map these anomalies and locate past strike locations. Analyzing the magnetized material can even provide insights into the characteristics of the original strike, like estimating its peak current. Maybe even tell if lodestones, natural magnets were formed this way.
That's amazing, tracing history and even power just from a magnetized rock. And the source mission, some really unexpected research linking lightning's magnetic fields to effects on people. Hallucinations.
Yes, this was fascinating. Some research, mentioned as coming out of the University of Innsbruck, has explored the possibility that the very strong but very short-lived magnetic fields generated by a severe lightning strike's plasma channel could be intense enough to induce temporary hallucinations in people standing relatively close, maybe within about 200 meters.
How would that work?
They draw a parallel to the effects sometimes seen in transcranial magnetic stimulation, TMS, where magnetic fields are used to stimulate brain activity. It's still theoretical for lightning, but an intriguing idea.
Hallucinations from lightning's magnetic field. That is genuinely unexpected and wild. Okay, with all these effects and the constant activity, how do scientists and weather services keep track of it all? How do they detect lightning?
Well, lightning detection and monitoring have a long history, starting with simple devices. Think Benjamin Franklin's lightning bell or Andrew Gordon's electric chimes back in the 1700s, which basically warned of static buildup before a storm hit.
Early warning systems.
Right. Modern detection is obviously highly sophisticated and relies primarily on detecting the electromagnetic radiation, those radio waves emitted by lightning flashes.
Using ground-based networks, primarily.
Yes. Ground-based systems are widespread, They use various techniques, often involving detecting those VLF waves we talked about.
The
It's guided by the Earth Ionosphere Waveguide.
And they triangulate the location.
By precisely timing the arrival of signals at multiple sensors, they can pinpoint the location of a strike, sometimes thousands of kilometers away. Comparing signal characteristics can also help determine if it was cloud-to-ground or intra-cloud, and estimate things like polarity and peak current.
And monitoring those global ELF signals, the Schumann resonances, tells us about overall activity.
Yeah, it tracks the pulse of global thunderstorm activity.
There are major networks covering whole continents now.
Exactly. There are nationwide networks in countries like the US, India, and Brazil, and multinational networks like EUCLID covering Europe. There are also global networks like WWLN, the Worldwide Lightning Location Network, Vesala's GLD360, a private commercial network, and even large volunteer or hobbyist networks like Blizzardtongue, a community effort. All these contribute to real-time maps of lightning activity that you can often see online.
So you can literally watch storms lighting up on a global map as they happen.
Oh.
What about from space? Satellites.
Satellite-based instruments provide an invaluable perspective, especially over oceans and remote areas where ground networks are sparse. Older instruments like the Optical Transient Detector, OTD, and the Lightning Imaging Sensor, LIS, provided long-term climatology data, helping us understand patterns.
And the newer ones.
The newest generation is really impressive. Instruments like the Geostationary Lightning Mapper, GLM, on NOAA's GOESR satellites, and the Lightning Imager, MTGLI, on Europe's Meteosat third-generation satellites, provide nearly continuous real-time lightning mapping over vast areas like the entire Western Hemisphere or Europe and Africa. They use sensitive near-infrared detectors.
That global real-time view must be powerful for forecasting severe weather and for research. Scientists can even create lightning for study, right? Trigger it.
They can, using artificial triggering techniques. The most established method is rocket-triggered lightning.
Shooting rockets into clouds?
Pretty much. Researchers launch a small rocket trailing a thin wire, often copper or steel, up into the base of a thundercloud during conditions favorable for lightning. The wire creates a preferential path and attracts a downward leader from the cloud. When the leader attaches, the wire essentially vaporizes in milliseconds due to the intense current, creating a controlled, relatively straight lightning channel that they can study in incredible detail with instruments on the ground. The International Center for Lightning Research and Testing in Florida is famous for doing this.
That sounds dramatic. And there's research into using lasers, too. A laser lightning rod.
Yes, that's been explored since the 1970s. The idea is to use powerful lasers. We're talking multi-terawatt infrared or UV lasers to create ionized channels in the air, essentially carving a path.
To guide the lightning.
Theoretically, yes, to guide or even trigger lightning discharges along that laser path. The ultimate goal would be to protect sensitive facilities like rocket launch pads or power stations by providing a predictable, safer path for strikes to follow.
Does it work?
Well, recent experiments have shown that lasers can enhance electrical activity in the air and generate small local discharges. But consistently triggering a full-blown lightning strike on demand and guiding it accurately with lasers is still an active area of exploration. It's not quite a practical lightning rod replacement yet.
The idea of a laser lightning rod is fascinating, though. Okay, let's talk about how lightning fits into the larger context of our changing planet. How is climate change affecting lightning activity? Is it increasing?
It's a really complex link and, frankly, hard to model precisely. Accurately simulating the cloud physics variables critical for predicting lightning, things like convection strength, and the amount and type of ice particles in clouds is still very challenging in global climate models.
No, we are seeing some trends or predictions, aren't we?
Yes, regionally there are some projections. Models suggest areas like Africa, which is already a major hotspot, might see a small overall increase in the total number of lightning flashes. However, the prediction is sometimes for fewer lightning days overall, but with more intense activity, more strikes occurring on those days when storms do form.
What about areas where lightning is less common traditionally, like the Arctic? You hear a lot about changes there.
That's a particularly interesting and concerning area. Observations are showing a notable increase in lightning activity in the Arctic.
Really, more storms up north.
Yes, and climate models project this trend will continue as the region warms much faster than the global average. The ratio of Arctic lightning strikes compared to global strikes is growing.
And what are the implications of that?
Well, it has significant potential feedback effects. For example, more lightning could ignite more wildfires in the boreal forests and tundra. These fires release carbon and could also impact permafrost thaw, releasing even more greenhouse gases.
A dangerous feedback loop. And air pollution plays a role too. Does smog affect lightning?
It can, yes. Particulate matter, or aerosols, from pollution, can influence cloud microphysics, how clouds form and behave. Up to a certain concentration threshold, aerosols can actually increase lightning activity.
How?
By altering ice formation processes and potentially enhancing charge separation. However, if pollution levels become extremely high, it can sometimes have the opposite effect, suppressing storm development and lightning.
So pollution can add fuel to the lightning fire up to a point, and lightning itself interacts with climate change, not just responds to it. It affects greenhouse gases.
Exactly. It's a two-way street. As we said, lightning is a major source of NOx, which leads to the formation of tropospheric ozone, and ozone is a greenhouse gas.
Okay, so more lightning could mean more warming from ozone?
Potentially. But lightning also produces chemical radicals in the atmosphere, like OH and HO2. These radicals are really important because they help break down methane, which is another very powerful greenhouse gas.
Oh, so it destroys the greenhouse gas too.
Right. So the net effect of a change in lightning activity on overall greenhouse gas concentrations and climate is complex. It depends on which of these processes dominates in different regions and how accurately the models capture these chemical interactions.
And that feedback loop with wildfires is concerning, especially with more Arctic lightning?
It is. Lightning is the single largest natural cause of forest fires globally, estimated to start maybe 10% or more of them. As lightning patterns change with climate change, particularly that projected increase in the boreal and Arctic regions, and as hotter, drier conditions make landscapes more susceptible to burning.
You get more lightning-ignited fires.
That's the concern, yes. And these fires, in turn, release more greenhouse gases and change the Earth's surface reflectivity, feeding back into the climate system. It's a really tangled web of interactions.
It really highlights how lightning is an active component of Earth's system, not just some passive weather effect we watch.
Yeah.
Stepping away from the science for a moment, lightning has obviously captured the human imagination for millennia. It's such a powerful image.
Absolutely. As a dramatic visual phenomenon, it was one of the earliest subjects of photography, which is kind of cool to think about. The first known photograph of lightning dates back to 1847 by Thomas Martin Easterly. The first surviving one is from 1882 by William Nicholson Jennings.
Capturing that fleeting moment. And culturally, it's so deep-rooted in religion and mythology across the world.
It represents immense unpredictable power, right? So it's easy to see why it was often associated with or seen as a manifestation of powerful deities across countless cultures. Zeus in Greek myth, Thor in Norse, Indra in Hindu, Perun in Slavic, Sango in Yoruba religion, Elapa in Inca belief, Reijin in Japanese Shinto. The list goes on and on.
Gods of thunder and lightning.
Exactly. Practices like divination from thunder and lightning, known as serenoscopy, existed in ancient cultures like the Etruscans. It holds symbolic significance in Judaism, Islam, and Christianity as well.
And it's given rise to famous myths, like the one about lightning never striking the same place twice, which is definitely not true.
Which the source material firmly debunks. That's absolutely false. Lightning frequently strikes the same place multiple times, especially tall, isolated, or highly conductive objects. The Empire State Building in New York City, for instance, is struck around 23 times per year on average.
23 times. Definitely strikes the same place multiple times. I love that the phrase love at first sight in French, coup de foudre, and Italian colpo di fulmine literally translates to lightning strike.
A perfect metaphor, isn't it? A sudden, overwhelming, unpredictable event.
Totally. And in political and military contexts, the thunderbolt symbol has been a potent representation of power, speed, and sudden force throughout history. You see it everywhere.
From ancient heraldry and national symbols to modern military unit insignia.
It's been used by various political groups wanting to project an image of strength or swift action. The source mentions the Singapore People's Action Party, but also historical groups like the British Union of Fascists and the U.S. National States' Rights Party. And it was incorporated into the SS SIG rune symbol.
A powerful, sometimes menacing symbol. And the term blitzkrieg, meaning lightning war, directly links the military concept of fast, decisive attack to the natural phenomenon.
The power of the symbol really speaks to the raw energy of lightning itself.
Definitely.
And for anyone whose curiosity has been sparked by this deep dive, the source material points to several related concepts to explore further things we touched on, like volcanic lightning, the still mysterious ball lightning, St. Elmo's fire, that faint glow. Upper atmospheric lightning like sprites and jets.
Those fulgurites we talked about, step potentials, terrestrial gamma ray flashes, TGFs, and lightning-induced remnant magnetism, LIRM. We dipped into many of these surprising related areas.
They all connect to the broader world of atmospheric electricity and discharge, showing just how much is happening above and around us, often unseen.
So we started with that familiar, dramatic flash and clap of thunder, and we've taken a deep dive into this incredibly complex, multifaceted natural event. We've seen how it's this furious interplay of charge separation driven by colliding particles you can barely see,
Creating plasma hotter than the sun.
releasing immense energy and having surprising impacts globally.
We've pulled back the curtain on the hidden steps, the stepping leaders you don't perceive, the upward streamers reaching from the ground, the hidden danger of step potential spreading out.
The subtle but permanent magnetic marks left on the landscape. It's amazing.
We've glimpsed how lightning influences atmospheric chemistry, acts as a natural fertilizer, how it links to cosmic rays, potentially produces antimatter.
And how scientists are actively trying to trigger it with rockets and even lasers.
It's a powerful reminder that even the most common natural phenomena hold layers upon layers of complexity and still harbor mysteries that scientists are working hard to unravel.
Definitely.
So here's a final thought for you to take away. The next time you see that brilliant flash pierce the dark sky, know that you are witnessing far more than just a weather event. You are seeing a fundamental part of Earth's global electrical system in dynamic action.
A force shaping our atmosphere, influencing our planet's chemistry and even geology, interacting with high-energy particles from deep space, and maybe, just maybe, creating antimatter in a split second.
It's a brief, violent burst, but it is profoundly connected to some of the largest and most unexpected processes happening on and around our planet.
Keep observing, keep questioning. There's always more to learn.
Welcome to the Deep Dive. Today we're plunging into a topic you probably have a pretty personal connection to. I mean, it impacts your life quite literally every time you eat or, smile. We are talking about dentistry. Now, you might just think of your dentist's office, right?
Yeah.
Fillings, cleanings, maybe that dreaded root canal. But the comprehensive article we're digging into today, our source material for this deep dive, it covers the history, the practice, the science, and it reveals a field with, well, incredibly ancient origins and connections that reach far beyond just your mouth.
That's exactly right. Our mission today is really to unpack this stack of information together. We want to pull out the most important insights, give you a real shortcut, to understanding the surprising depth and, frankly, the critical importance of this field.
Yeah, get ready to maybe have some assumptions challenged. We're talking dentistry being practiced millennia ago with really rudimentary tools and ancient beliefs that some had persisted for centuries. And this powerful connection our source really highlights between your oral health and, well, your entire body.
Okay, let's unpack this then. So let's start right at the beginning. Our source defines dentistry not just as, like, fixing teeth, but as a branch of medicine.
Exactly. It is a medical field, but one specifically focused on the oral cavity.
Okay, the oral cavity, so teeth, gums, mouth.
Pretty much. And what's interesting, it also includes related structures, things like the craniofacial complex.
Craniofacial complex. Okay, that sounds a bit complicated. What does that really cover?
Think bones and tissues of your head and face, basically.
Right.
So dentistry scope actually extends to areas like your jaw joint.
Ah, the TMJ. People talk about that.
That's the one, the temporomandibular joint. And the practice itself, it's broad. The source says it covers study, diagnosis, prevention, management, and treatment of diseases, disorders, conditions affecting the mouth. Mostly, yeah, it focuses on the teeth, the dentition, and the oral mucosa, the lining of your mouth. But it's really about that whole system in there. Got it. And the person steering the ship here is the dentist. The material also mentions odontology. What's that exactly?
Right, odontology. That's the associated scientific study. Basically, the science behind the teeth, how they grow, their structure, what goes wrong, the abnormalities.
Okay. And historically, this was a surprise in the source. European dentistry seems to have stemmed from barber surgeons.
Isn't that something? Yeah, barber surgeon. I mean, can you imagine? The person cutting your hair might also be pulling your tooth.
Wow.
It really highlights those very hands-on early roots.
And the dentist isn't usually flying solo, right? The source talks about the dental team.
Oh, absolutely. The
Yeah.
team is crucial. You've got the dentist plus the dental auxiliaries.
Auxiliaries like, well, you have dental assistants working right there with the dentist, dental hygienists focusing on cleaning and prevention, which is huge. Then dental technicians, the ones in the labs making crowns or dentures, and dental therapists who can do certain procedures, often under supervision.
Makes sense. And we find these teams in different places. Yep. The source lists private practices. That's the primary care setting most of us know. But also dental hospitals or institutions, places like prisons or on military bases.
Okay. Now let's rewind, like way back. This history section of the source is just, it's incredible. How ancient are we talking?
It really puts things in perspective, doesn't it? We're talking evidence dating back between 7000 BC and 5500 BC.
Whoa, okay, so almost as old as, like, settled human civilization itself.
Pretty much. And the material gives some amazing examples, like this site in the Indus Valley, Mehrgar. Around 7000 BC, they found evidence suggesting people used bow drills for tooth disorders.
Bow drills,
Yeah.
like for starting fires or making beads.
Exactly. The theory is that skilled bead crafters might have been the ones doing this early dental work, based on the tools found there.
That's wild, using bead drills on teeth. And did it? Did it work?
Well, reconstructions showed the methods were, surprisingly reliable and effective for that time.
Incredible, and there's more.
Oh, yeah. There's a 14,000-year-old tooth from Italy. It shows signs of being partly cleaned with flint tools.
14,000 years. That could be the oldest known manual dentistry.
Possibly. And the source even mentions a study suggesting Neanderthals might have used rudimentary tools for dental self-care like 130,000 years ago.
Mind-blowing. So it wasn't just cleaning.
No, not just cleaning or drilling. The material points to early attempts at fillings, too.
Fillings, what do they use?
Get this. Bitumen. In Paleolithic Italy around 13,000 years ago, and beeswax in Neolithic Slovenia about 6,500 years ago.
Beeswax fillings.
And there's even evidence from prehistoric Malta, maybe 2,500 BC, of a dental abscess that was lanced, like a form of surgical intervention.
So people were actively trying to fix problems, not just endure them.
Right, and trying to understand why they happened. The source really highlights this ancient Sumerian belief. The toothworm.
Ah, the toothworm. I've heard of that. The idea that a worm burrowed in and caused decay.
Exactly. And what's fascinating is how widespread that idea was. It wasn't just Sumeria. It popped up in ancient India, Egypt, China, Japan. Even in Europe, it persisted. Right up until the 14th century AD, promoted by surgeons like Guy de Chauliac.
Wow. That shows how a simple, visible problem like a cavity could lead to these explanations that just stuck around for ages, even if they were wrong.
Totally. And ancient texts give us more glimpses. Egyptian papyri had recipes for toothache, infections.
Practical stuff.
Very practical. The Edwin Smith Papyrus, 17th century BC, it discussed treating fractured jaws, a proper surgical manual for its time. Even the Code of Hammurabi, 18th century BC, mentioned dental extraction, though as punishment in that case.
Ouch.
Yeah. And people were already attempting prosthetics, using gold wire to stabilize loose teeth in ancient Egypt and Greco-Roman times, or actual dentures crafted by Etruscans and Phoenicians using gold bands and ivory, or even animal teeth sometimes.
So the idea of replacing missing teeth isn't new at all. They were already thinking about fixing broken mouths thousands of years ago.
Absolutely. And moving forward a bit, the source notes early amalgam fillings being documented in Tang Dynasty China, 7th century, and then appearing in Germany in the 16th century.
Amalgam, like the silver fillings. That early.
Seems so, yeah. And the Islamic Golden Age saw huge contributions. Physicians like Avicenna described ways to reduce jaw fractures by lining up the teeth, a method that's still, fundamentally sound. And Al-Zarawi invented surgical instruments that look remarkably like some modern ones.
It's clear, though, throughout history, just pulling a bad tooth was common, often by those barbers or general physicians you mentioned.
Right. And the tools evolved. From the medieval dental pelican.
The what?
The dental pelican, it was an extraction tool. Then later the dental key, which kind of looked like a door key, eventually leading to the forceps we'd recognize today, which became standard in the 19th century.
And the knowledge started getting written down more formally.
Yep. The first book just on dentistry, the Arts Buchlein, that was 1530. And the first English textbook, Operator for the Teeth, 1685.
But even with books, it wasn't quite a formal profession everywhere yet.
Not for a long time. The source points out in the UK, for example, no formal qualification was needed before 1859. And it wasn't until the Dentists Act of 1921 that practice was actually restricted only to qualified practitioners. Took a while.
Okay, so that brings us to what the source calls the dawn of modern dentistry, roughly 1650 to 1800.
That's the key period. And one name really stands out here, Pierre Fauchard.
Tramshar, right? The
Mm.
father of modern dentistry. What made him so important?
Well, he was a surgeon working with pretty primitive tools by our standards, but he had incredible ingenuity. The source details his impact. He was apparently brilliant at improvising instruments, adapting tools from like watchmakers, jewelers, even barbers.
Resourceful.
Totally. And he introduced dental fillings as a standard way to treat cavities. He also had this remarkably early insight into decay. He proposed that sugar-derived acids, he mentioned tartaric acid specifically, were the culprits.
That's pretty advanced thinking for the early 1700s.
It really was. And he pioneered dental prosthetics, too, making substitutes for lost teeth from carved ivory or bone.
And braces.
Yes, introduced dental braces, initially using gold and threads, waxed linen, or silk to guide teeth into better alignment.
Amazing. But maybe his biggest contribution was the book.
Absolutely. Le Chirurgien Dentiste, 1728. It was the first truly comprehensive text. It pulled together all the existing knowledge and techniques, and crucially, it argued for dentistry as its own distinct field, separate from general surgery. That was huge.
Okay. Any other key figures from that era mentioned?
Yeah, the British surgeon John Hunter. He wrote influential books in the 1770s about teeth and treatment. He actually collaborated with the dentist James Spence, and they explored tooth transplantation.
Transplanting teeth back then.
Yeah. Hunter theorized that success depended on the donor tooth being fresh and a good-sized match, which, believe it or not, kind of echoes the basic principles behind modern organ transplantation.
That's incredible. Did it work?
The source notes one of his patients had 3 transplants that apparently lasted for 6 years. Pretty remarkable for the time.
Wow. Okay, so by the 19th century, things are really picking up steam.
Yeah.
The profession is gaining ground.
Definitely. It started coming under government regulation, like that UK Dentist Act in 1878. And a big step for its status, the source mentions, was when Francis Brodie Imlock, a dentist, was elected president of the Royal College of Surgeons in Edinburgh in 1879.
So putting dentistry on par with clinical surgery, at least in that context.
Exactly. A major moment.
Okay, here's where it gets really interesting, I think. Let's jump forward to dentistry today.
Right.
What are the main battles being fought, in the modern mouth?
Well, according to our source, the big 2 are still dental caries, cavities, tooth decay, and periodontal disease, which is gum disease.
Still the main culprits after all this time.
Yep. And the World Health Organization says these are major public health problems globally. Significant burden.
So what can your average general dentist do about these? What's in their toolkit?
The source lists quite a bit. There's restorative work fillings, crowns, bridges, basically fixing damaged teeth. Prosthetic work dentures, implants maybe replacing missing teeth. Endodontic therapy, that's root canals, dealing with the inside pulp of the tooth. Periodontal therapy for gum issues, extractions of course. Plus exams, taking x-rays, diagnosis, and prescribing medications like antibiotics or sedatives.
Okay, quite a range. But the source also says some things need extra training.
Right. Depending on the specific license and location, things like providing sedation or placing dental implants might require additional specialized training beyond general dental school.
And speaking of specialized training, there's a whole world of dental specialties out there now, isn't there?
Oh, yeah, absolutely. Dentists can pursue years of further training after dental school. The list of specialties is long, and it can vary a bit by country.
Give us a few examples just to get a sense of the breadth.
Sure. You've got oral and maxillofacial surgery, that's complex stuff like jaw surgery or fixing facial trauma, orthodontics for straightening teeth, braces, and aligners, pediatric dentistry, specializing in kids, endodontics for complex root canals, periodontology, the gum specialists, prosthodontics for advanced restorative work and replacements.
Wow, okay. It keeps going.
It does. There's even forensic odontology using dental evidence in legal cases, sports dentistry, veterinary dentistry, yes, for animals, and even super specialties like maxillofacial prosthetics, which deals with reconstructing parts of the face after, say, cancer surgery or trauma. It's incredibly specialized.
It's amazing. But maybe one of the most crucial things the source brings up is this idea of oral systemic health.
Yes, this is absolutely key. Cannot stress this enough. It means your oral health isn't just isolated to your mouth, it's profoundly connected to your overall bodily health, your general health.
How so? What kind of connections are we talking about?
Well, the source highlights that conditions in your mouth can actually be signals. indicators of systemic diseases happening elsewhere in your body.
Like what kind of diseases?
Things like osteoporosis, diabetes, certain types of cancer, even HIV/AIDS can sometimes show early signs in the mouth.
That's powerful. So your dentist might actually spot something that points to a bigger issue you weren't even aware of.
Exactly. And the source gives this really specific, striking example: irreversible enamel defects on your teeth. Sometimes these defects can be the only initial clue for celiac disease, even if the person has zero gut symptoms at that point.
No way, just from looking at the teeth.
Yeah. And these defects can easily be mistaken for other things like fluorosis or just developmental issues. But a knowledgeable dentist seeing that pattern, as outlined in the NIH protocol the source mentions, might be the first person to suggest looking into celiac disease.
That's incredible.
It is, and it goes the other way too. Gum disease itself, periodontal disease, isn't just a local problem. It's associated with an increased risk of developing or worsening conditions like diabetes, heart disease, and even complications in pregnancy like preterm birth.
Wow. Okay, that completely changes how you think about a regular dental checkup, doesn't it? It's not just about scraping plaque off your teeth. It's potentially a window into your overall health.
Precisely, which underscores why prevention is so critical. Good hygiene at home, yes, but also those regular professional cleanings and evaluations, they're vital.
Okay, let's touch briefly on education. How does someone become a dentist? Does it vary much?
It varies quite a bit globally, actually. The source mentions it often involves 5 to 8 years of study after high school or secondary school, sometimes even more for postgraduate qualifications and specialties. In the U.S., the typical path is an undergrad degree, then 4 years of dental school to get a DDS or DMD degree.
And the UK has different degrees, like BDS.
Right, Bachelor of Dental Surgery, things like that. And interestingly, the source notes that where a dentist trained can sometimes influence their clinical decisions.
How so?
It gives an example about wisdom teeth removal. Apparently, dentists trained in Israel might approach the decision differently than those trained in parts of Latin America or Eastern Europe, even when looking at similar patient conditions. Just different clinical philosophies sometimes.
Interesting. Now, the material also brought up some maybe less discussed aspects of modern practice, like occupational hazards, noise exposure.
Yes, that's an important point. Those dental tools, especially the ultrasonic scalers used for cleaning, they generate noise.
Right, that high-pitched sound.
Exactly. And while one appointment's worth might not seem like much, the source explains that for the dentist, that prolonged exposure over an entire career, it can add up. It can contribute to noise-induced hearing loss, NIHL, and tinnitus, that ringing in the ears.
Are there safety limits?
Oh yeah, official guidelines exist, like OSHA and NAOEDGE levels for workplace noise. But the source points out that, maybe surprisingly, relatively few dentists consistently report using hearing protection.
Even though the cumulative effect over years could push them over those safe limits, or at least contribute to hearing issues.
Potentially, yeah. Even noise below the official limits, if it's constant day after day, can take a toll over time. Something to be aware of.
Okay. On a more positive tech note, digitalization is a big theme the source mentions. How is technology changing dentistry?
Oh, it's changing it quite a bit. We're seeing things like CAD/CAM systems becoming more common.
CAD/CAM.
Computer-aided design and computer-aided manufacturing, often linked with 3D printing. It allows dentists to design and sometimes even mill crowns, bridges, or other restorations right there in the office, much faster than traditional lab methods.
That sounds efficient. What else?
Artificial intelligence, AI, is also entering the picture, being explored for things like helping diagnose issues from x-rays or scans, treatment planning. And electronic health records, of course, are streamlining how patient info is managed and shared. The overall aim is better effectiveness, accuracy, and maybe patient experience.
So is every dental office using all this fancy tech now?
Not quite universally, no. The source says adoption varies. You tend to see it more in larger dental centers, maybe with younger dentists who train with digital tools, and those who specifically sought out digital training opportunities.
What are the holdups for others?
The material identifies a couple of main barriers. One is just financial cost. This tech can be a significant investment for a practice. And the other is the need for really comprehensive training. It's not just plug and play. Practitioners need good training to use it effectively and confidently.
Makes sense. And finally, the source just briefly touches on ethics and legal stuff.
Yeah, just reinforcing that dentistry, like all healthcare, relies on competence. Clinical skills have to be built through proper supervised training. It also underlines the need for dental care to be grounded in research and evidence, not just tradition. and how accreditation systems for schools and professionals help ensure quality.
Okay. So what does this all really boil down to? We've gone from, prehistoric folks trying to clean teeth with flint and believing in tooth worms through figures like Fauchard really formalizing the field to today's world of high-tech tools, specialized practices, and this really powerful understanding of the link between the mouth and the whole body.
Yeah, it really paints a picture of dentistry as this deep, complex, constantly evolving, and truly critical branch of medicine. It's so much more than just fixing teeth.
Absolutely. Well, thank you for joining us on this deep dive into the world of dentistry.
And maybe something to leave you thinking about. Considering this incredible long history of human ingenuity in tackling oral problems, from ancient myths to modern science connecting the mouth to systemic health, and with technology changing things faster than ever, what more might we still uncover? What new understandings might emerge about the fundamental role the mouth plays, not just in our physical health, but maybe even in our very definition of well-being? All right, let's dive in today. We're talking about plunging into the unknown, basically following a coded message from a 16th century alchemist.
And finding an entire prehistoric world hidden, miles beneath our feet. It's pretty wild stuff.
Absolutely. We are strapping in for a deep dive into Jules Verne's just absolute iconic adventure, Journey to the Center of the Earth.
Yeah, and our map for this whole thing is, a detailed look at the novel itself. We're going to focus on the story, the characters who were fascinating, the ideas Verne was playing with.
Yeah, and how this incredible tale has just fueled imaginations for, over a century now?
Easily. It's huge.
Think of it as navigating through Victorian science, real daring exploration, and just pure unadulterated fantasy. We're talking volcanic tubes.
Underground oceans and things that, it really shouldn't exist anymore.
It's kind of a shortcut to understanding why this particular book still holds such a powerful grip on pop culture,
Right. So grab your pickaxe, maybe your courage. Let's descend. Okay, so at its heart, this is Voyage au centre de la Terre. That's the original French title, by the prolific French writer Jules Verne.
And it first came out in French back in 1864, but the version most people know, that's the revised and expanded edition from 1867, right?
Exactly. And it sits squarely in that sort of fantastic blend of science fiction and adventure. It's part of his big Extraordinary Voyages series.
Now, subterranean fiction going underground in stories, that wasn't totally new, but Verne did something really innovative here.
Yeah, that's key. What really made Verne's novel stand out, even back then, was this incredibly clever mix of seemingly well-researched Victorian science.
Like what they understood about geology and fossils at the time.
Right. Combined with this truly groundbreaking concept.
Yeah.
The idea that a thriving prehistoric realm could still exist hidden away right now in the present day.
That wasn't something people were really exploring before Journey.
Not in the same way, no.
It wasn't just going underground. It was like finding a time capsule the size of a continent down there.
Okay, so where does this whole kind of insane idea even begin?
Well, it all kicks off, rather, domestically, weirdly enough. May 1863. We're in the home of Professor Otto Lidenbrock in Hamburg, Germany. A bit chaotic, apparently.
And Professor Lidenbrock, he's quite the character, isn't he? He's painted as this incredibly eccentric German scientist, a geologist specifically.
Who also happens to have a notoriously hot temper.
Yeah, and these really radical ideas for the time, like the possibility of volcanic tubes reaching all the way down to the Earth's core. Heretical stuff.
And contrast him with his nephew, Axel. Young student, much more grounded, way more cautious than his uncle.
He's basically dragged along for the ride, isn't he? He kind of provides that necessary dose of, reality and maybe anxiety, faced with Lidenbrock's relentless drive.
Definitely. So they stumble upon the catalyst for everything. Lidenbrock gets hold of this ancient runic manuscript. It's an Icelandic saga.
And tucked inside, he finds this ciphered note. A note that, tantalizingly, is attributed to a real person. Arn Saknussemm, a 16th century Icelandic alchemist.
Implying that this guy, centuries ago, might have actually made this journey somehow.
Exactly. In the note itself, it's basically an instruction manual, a very cryptic one, mind you.
Oh, you have to hear this. This is the translated text that sets everything off. Go down into the crater of Snæfellsjökull, which Scartaris's shadow caresses just before the calends of July. O daring traveler, and you'll make it to the center of the earth. I've done so. Arne Saknussemm.
I mean, talk about a call to adventure, right? And for Lidenbrock, there's zero hesitation.
None. Despite Axel being obviously reluctant, Lidenbrock is immediately booking passage. They're heading for Iceland. Through Kiel, Copenhagen, finally landing in Reykjavik.
And in Reykjavik, they make a really crucial addition to their team. They hire Hans Bielke, an Icelandic eiderduck hunter. He's described as incredibly resourceful and, maybe more importantly, just imperturbable, totally unfazed.
You need someone steady when you're doing something this crazy.
Absolutely. So from Reykjavik, they trek overland to the base of this inactive volcano, Snæfellsjökull.
They find the exact spot from the cipher, and, well, they begin their descent down into the volcano's dark interior, following Saknussemm's trail.
And the journey down is anything but smooth. Immediate dangers. You've got cave-ins, sections of tunnel collapsing.
Even these weird subpolar wind currents like underground tornadoes.
Yeah, and then there's that really nail-biting moment, the water crisis. They just run out desperately. Axel is basically dying of thirst in the heat down there.
This is where Hans really shines, isn't it? His quiet resourcefulness saves them. He finds and taps into a subterranean river.
And Lidenbrock and Axel, in this rare moment of joint gratitude, they name it the Hansback.
A well-deserved honor. But the perils, they're not over. There's that terrifying bit where Axel gets separated during a rock slide.
Oh yeah, lost alone in the dark caverns, just calling out echoes. It's chilling. Before they finally manage to find him again.
And then, after enduring all that, the claustrophobia, the danger, they break through. And they find, well, a world. A vast, unimaginable space deep underground.
It's incredible, the description. An ocean so big, Lidenbrock christens it the Lidenbrock Sea.
And above it, it's not solid rock. It's like a cavern ceiling that looks like a sky, complete with clouds.
And lit by permanent aurora, it provides this constant light.
Amazing. And they build a raft, right, out of fossilized wood they find just lying around to sail across this underground ocean.
And this is where Verne really lets loose with the prehistoric wonders, drawing heavily on the paleontology of his day,
Right. Sailing the sea, exploring the shores. They encounter creatures that science says should be long, long extinct.
Like strange mammal-like creatures on the shore. You've got gazelle-like things, cattle-like, tapir-like, even a huge ground sloth, a megatherium.
And flying overhead, pterodactyls.
But the real drama is in the water. They spot these ancient fish and, most thrillingly, giant marine reptiles from the age of dinosaurs.
Yeah, the big ones. Ichthyosaurus and Plesiosaurus. The source highlights this really pulse-pounding scene where they actually witness a brutal fight between these two monsters.
A battle that threatens to swamp their tiny raft. It's Verne tapping into that huge public fascination with these newly discovered fossils.
Totally. What if? What if these things were still alive down there?
Exactly. And the adventure continues. There's this massive lightning storm that erupts over the underground sea.
Which sounds absolutely terrifying. But instead of destroying them, it washes them ashore somewhere new. An enormous fossil graveyard.
And this graveyard, it's just packed with bones. Pterodactylus, Megatherium, Dinotherium, Glyptodon, mammoths, like a treasure trove of prehistory.
And amidst all the bones, something even more unexpected.
A body. A preserved body of a prehistoric hominid.
But the real jaw-dropper comes a bit later, doesn't it? When they explore a forest from the Tertiary period, full of primitive plant life?
Yes. They encounter a living humanoid, described as over 12 feet tall.
Which is huge.
Massive. Huge. Unshapely head. A mane like a prehistoric elephant. And it's wielding a primitive staff. It looks like it's herding mastodons, like a shepherd.
That is, yeah, unsettling is the word. And understandably, Lidenbrock and Axel decide, okay, maybe time to leave. They fear this giant might not be too friendly.
It's a moment where Verne really stretches the limits, even of his own fantastical science,
Definitely. So, after surviving all of that, how do they actually get out of this incredible underground world?
Well, they finally find a passage that Arne Saknussemm marked as the way forward. But, of course, there's a catch.
It's blocked. A recent cave-in.
So their solution is pretty dramatic. Gun cotton. A powerful explosive. They're going to blast through the rockfall.
They paddle their raft out onto the sea first, right? To get some distance from the blast.
A smart move. But the explosion works. Maybe a bit too well. It doesn't just clear the passage.
No, it opens up this huge, seemingly bottomless chasm beyond the rockfall.
And in this truly wild twist, the entire underground sea starts rushing down this new abyss. and they're swept along with it.
Just plummeting for hours into this void. Falling, falling.
Until the raft suddenly reverses direction.
Hmm.
It starts rising incredibly fast up inside a volcanic chimney.
The ultimate, completely unplanned extraction method.
Totally. They get ejected, unconscious, right out of the mouth of an active volcano.
And when they wake up, where are they? Stromboli, a volcanic island way off the coast of Sicily. Talk about a journey.
Geographically and conceptually, yeah. So, back on the surface, they eventually return to Germany as heroes.
Professor Lidenbrock is hailed as this great scientific visionary. His radical ideas are spectacularly validated, you know.
Right. And Axel has his own little moment of discovery. He figures out their compass poles reversed during that crazy lightning storm underground.
Ah, solving that navigation puzzle they had. And he gets his happy ending too, doesn't he? Marries Greiben, Lidenbrock's goddaughter, who we met briefly earlier.
He does. And loyal, imperturbable Hans. He just goes back to his peaceful life in Iceland. His job is done.
Now, the story doesn't just end there on the final page. This book has had a seismic impact on literature, on popular culture.
Yeah, as we touched on, that core innovation, the preserved prehistoric world mixed with plausible for the time science, that was huge. It directly inspired later authors who picked up that thread.
Right, people like Sir Arthur Conan Doyle. The Lost World owes a lot to this. Edgar Rice Burroughs and his Pellucidar series, the Hollow Earth stuff.
You can even see echoes of it maybe in the underground journeys in Tolkien's The Hobbit.
That's interesting. It's also fascinating to look at the publication history, especially those early English translations. The first one, 1871. It took enormous liberties.
Oh yeah, changed character names completely. Lidenbrock became Hardwig, Axel was Harry, Graben was Gretchen, and it significantly rewrote whole sections.
And even the 1877 translation, the Malison one, which was more faithful, it still made changes, added chapter titles, tweaked details.
It really highlights how different early readers' experiences of Verne could be, compared to the modern, more accurate translations we have now.
But where you really see the novel's reach is just the sheer range of adaptations. The story just begs to be visualized, doesn't it?
Absolutely. Film is a big one. That 1959 movie with James Mason, probably the most famous early one.
But notorious for its changes, moving the start to Scotland, swapping names again.
And famously using, like, iguanas with fins glued on for dinosaurs.
Right, and adding totally new characters and subplots. It was its own thing.
Then the 2008 film took a different tack, using Verne's book itself as the spark for a modern adventure. Female guide, different creatures like a Giganotosaurus.
And there have been others too. TV miniseries, even low-budget versions like the one from the Asylum.
It's gone to television, radio. The
Yeah.
BBC's done several serials over the years. NPR did one too.
Even theme parks. There's that major high-speed dark ride at Tokyo Disney Sea based on the book.
And Verne's work generally, including this story, really influenced areas at Disneyland Paris, like Space Mountain in its original form.
The list just keeps going, right? Comics, video games going way back to the 80s, board games, audiobooks read by famous actors.
Rick Wakeman did concept albums based on it, 2 of them.
Wow. And cultural references just pop up everywhere. Doc Brown in Back to the Future, huge Verne fan.
There's that character Skartaris in the Warlord comic series, named after the mountain peak in the book.
And even a Nobel laureate, Haldor Laxness, set his novel Under the Glacier near Snæfellsjökull and referenced Verne. Shows the almost mythical status the volcano got from the book.
So what really makes this story endure? Why does it keep getting told and retold, do you think?
For me, it's that perfect fusion. Scientific curiosity, the thrill of exploring the Earth itself, combined with this just boundless imagination that says, what if the impossibly ancient is still just waiting to be found?
Yeah.
It taps into that fundamental human impulse, doesn't it? To explore, to discover what's over the next horizon, or in this case, under the next rock layer, even when, conventional wisdom says it's impossible.
It really makes you wonder about the unexplored spaces that might still exist, even in our seemingly mapped-out world today.
So we've journeyed from a professor's study in Germany, plunged down a volcano in Iceland, sailed a luminous underground ocean, dodged prehistoric monsters.
That got shot out of a volcano in Italy.
All tracing the path of a story that has inspired generations of writers, filmmakers, adventurers.
It's a testament, really, to the power of a daring premise and characters who are just willing to follow it wherever it leads.
Absolutely.
And it kind of leaves you with this thought, doesn't it? As our science gets better, letting us probe deeper into the Earth or look further into space, What truly unknown frontiers might still be out there? What incredible, maybe even prehistoric or just completely unimagined wonders might still be waiting for us? Not just in books, but maybe in reality.